So let's take a minute and talk about transformers. And this will give us a chance to review the magnetic field in a solenoid and kind of connect a few things together. Should be useful for your homework. So what is a solenoid? Um, Remember, this is just a coil of wire. So we can draw a cartoon of it like this. And we had talked about how, if there's a current that's flowing through this, imagine the current is flowing through that way. You can use the right-hand rule then to figure out what direction the magnetic field would be. And so for the way that I have it drawn in here, that would mean that the current is coming out over here. You can see that if you apply the right-hand rule, that would mean that the magnetic field would be going to the left. Draw that here. And we talk about how the magnetic field is basically uniform in the middle of the solenoid. And we came up with the expression for that magnetic field that it's equal to actually mu times, sometimes you see this as mu times little n, where little n is the number of turns per length, but we're just going to leave it as number of turns per length times the current. So if you increase the current, you increase the magnetic field. If you increase the number of turns, you increase the magnetic field, etc. So just to label these pieces, this is the permeability, the magnetic permeability. And just for reference, if you don't have anything, any sort of metal ferric core or anything, this would have a permeability of just a free space, which is 4 pi times 10 to the minus 7. So this is the number of turns. This is the length. And this is the current. This is our expression for the magnetic field of a solenoid. Now, more recently, we've been talking about flux, and the magnetic flux, remember, is the magnetic field times the area. So if you imagine this coil has an area, like a cross-sectional area of A, then we can determine the flux for the solenoid in the middle of the solenoid would just be, our expression times A. And then most recently, we've been using Faraday's law that a changing magnetic flux is responsible for generating a voltage, an EMF. So, and that expression was this, where it depends on the rate of change of the magnetic flux. So we can kind of put these ingredients together. So this was Faraday's law. If we put these ingredients together, find that, I'll just write it like this. Notice most of this is constants. You're not going to be changing usually the area of the coil or changing the number of turns or something like that. You can imagine kind of, problems where you can do that, and there are some things like that in the homework. But generally, if you're talking about a coil, the thing that you're worried, that you're going to change is the current. And so you could factor out all that stuff, and notice you get a factor of n squared. It's mu over L times the area. Really, the only thing that's changing is the current. And it turns out that this stuff is something called the inductance for a solenoid. And you can think of this as very analogous to capacitance. So, in other words, the inductance is related to the amount of flux that you get per unit per current. So it's analogous to how capacitance is, recall that was the amount of charge per unit voltage. And kind of what's qualitatively, big picture. If we had more time, we would go into a lot more detail about this. But when we were talking about capacitors, we were talking about, electric, or we were talking about energy stored in an electric field. Well, when we're talking about inductors, you can store energy in a magnetic field. And we'll talk about this a little bit, but we're not going to be able to go into a lot of detail. But the thing that I want to show you is, notice you're not going to have any voltage unless you have a change in current. And this is a big part of why AC has come to dominate. And let me show you an example to try and motivate this. So this is part of what makes AC so useful. So imagine for a moment, again, we'll think of a solenoid, except now you're going to wrap it around like a common iron, like, core. Try and draw this here. So this is going to be okay. And over here it's kind of the same deal, except it does not have to have the same number of turns. It doesn't look very good. Let me try this. Okay. So, this would have some number of turns and this would have some other number of turns, and you could imagine putting, voltage in over here and voltage out over here, and this is generally called the primary. This is kind of fat. Let me primary and the secondary winding. And so we were just talking about how, the voltage looks like, according to Faraday's law, the change in flux per time. You have to have a change in current in order to cause that in the solenoid example. But just backing up for a second and just talking about the flux generally, if you make this out of a highly permeable magnetic material, you're basically going to get the same or very similar flux in both coils. And so what that means is that the voltage in 2 would look like this. And but the fluxes are the same. So we could solve this for flux. And notice if these are equal to the same flux, then these are equal to each other. And what does that mean? Well, the ratio of the voltages is equal to the ratio of the turns in the windings. And this device is called a transformer. And why it is so useful is that you can, and why AC current is so useful is that you can use it to change the voltage. So let me give you a couple examples. Just for to try and this is, I would note this is in section 29.6. So suppose, let's see here. You know, if the primary winding had 10 windings and the secondary winding was 100, and if you put in, you know, 12 volts, then we could solve this for the voltage on the secondary. Oops. And you can see that, you know, if we just put in our numbers here, 12 times 120 volts. So in this case, if you put more windings on the secondary, you can increase the voltage. So this is a what would be known as a step-up transformer. And similarly, those little wall warts like you have on your computer. With your computer, it's sort of the little brick thing. And you know how those are always sort of heavy? That's because they have that, they have a metal, generally, they have a metal component for the magnetic flux, and that's where the weight is coming from. So think of a wall wart or like a, computer power supply. So generally, let's just imagine it's like a little box and it's got that you plug into the wall. And this would be 120 volts, the wall voltage. And what's coming out of this can be combinations of things, but for example, 5 volts. If you look at your computer power supply, it may have multiple windings, or those are probably more complicated circuit that has solid state voltage conversion stuff in it. But for sake of example, assume it's a 5 volt supply, or we're looking at one of the 5 volt windings. You can ask a question about, like, well, what turns ratio would you need to get 5 volts? And notice this is by definition an AC current, because if it were DC, you would have no di dt, and you would have no changing magnetic flux. So in order for this to work, it has to be DC, or sorry, AC. Actually, let me put that in red. Put it this way. This only works with AC. And so this is part of the motivation, part of the reason that AC has become so ubiquitous is because of this. So But to this question of, what turns ratio would you need? Well, if the wall voltage is 120 and your voltage is 5, then this is a factor of 24. So N1 over N2 would be 24. And so that means that if N1 was 100 windings or something, N2 would be 2400. So it gives you an idea of the kind of thing that this is useful for. One other thing that I want to mention for why this is why AC just generally is so useful is this is used in transmission. So what I mean is, your book talks about this as well, but kind of the cartoon picture is, you have a power plant, and you don't just have a generator that spits out a voltage and then send that out to people. You have a step-up transformer. And then you have your transmission line, and then you have a step-down transformer. And then it goes to the load, to your house or whatever. And the reason for that is because this can save a huge amount of power that would otherwise be lost in the transmission line. So you know that this has some resistance. And if you want some amount of power to go to your load, generally the power is going to be the current times the voltage. Well, if you step up the voltage, the current has to go down. Okay. And the power that's going to be lost in the line to deliver whatever amount of power you need to. Let me put it this way. It's going to depend on the current and the resistance. So, for example, and it depends like I squared. So if you step up the voltage by a factor of 100, that would mean the current would step down, would be less by a factor of 100. But the power lost would be 1/10,000th. So it's way less. And this shows, part of the power, and a giant wire doesn't have very much resistance, but if you're sending power miles and miles, through a transmission line, this is, this gets at the usefulness of a transformer. And it also gets at, if you're sending power very long distances, those will be high voltage transmission lines, and they'll be at even higher voltage uh, uh, than sort of neighborhood transmission lines. So like a local transmission, like around houses and stuff, is maybe on the order of like 10,000 volts. But long distance lines can be much higher. Like I've seen numbers quoted 345,000 plus volts. That's 345 kilovolts. It's a lot of, it's a high voltage. And that's why those poles are so tall and so far away from stuff, right? You wouldn't want to have an accidental discharge.